In this video, I'm going to talk about modularization in tree-structured undirected graphical models. The resulting algorithm is called the sum product algorithm, which I'm going to sketch where it comes from. So, as a reminder, we have for a tree over vertices or nodes V and edges E, so the nodes are going to be 1, 2, up through n, which each node corresponds to a random variable, so x1 up through xn. The distribution for x1 up through xn factorizes into the product of these node potentials times the product of these edge potentials. Okay? What we want to do in modularization is we want to compute the distribution pxi for every node I. Okay? And so sum product is going to give us a way to compute these efficiently. The general idea will be that, well, to compute one of these guys, I'm going to sum out all the x's except for xi. Okay? So let's work through an example of this. Okay, so here we have this tree over 5 nodes. So the distribution from x1 to x5 factors as follows. This is just the equation I wrote before, specialized to this graph. The equation's kind of long, so I've split it into 3 lines. Okay? And so what we want to do here is we want to compute the marginal at x1. Okay? And so what we do is, well, we're going to want to sum both sides of this giant mess over x2 up through x5. So we do that for both sides. And by doing that, this will exactly give us a marginal at x1 after we've done the summation. Okay, so the idea behind the sum product algorithm is very simple. We're just going to push in these summations as far as possible. Okay, and so for example, let's start with x5. Well, there are only 2 terms that depend on x5, this phi5 of x5 and this psi25 of x2, x5. So why don't I move the phi5, x5 over to the end here, and then we have this summation over x5. So now this thing only goes to x4. Okay, so we'll have this after we push in the summation over x5, and we'll call this quantity right here, we'll call this m5 to 2. Meaning that we're summing out x5, and the resulting thing is going to be just a function of x2. Okay, so this is just some notation we're introducing, and to foreshadow, this m is going to stand for a message. Okay, so this will be like a node passing a message to another node. Okay, so the next thing we could do is we notice, oh, we can also push in the summation for x4, where the only 2 terms are this phi4 and psi24. So I'm going to repeat what I just did. Going to push in the summation for x4, and I'll have these 2 terms here. Okay. And we'll call the message from 4 because we're summing out x4 to 2 because this thing's going to be a function of x2. Okay, the next thing is we note, oh, we could repeat the same thing with x3. There are only 2 terms that depend on x3, so why don't we go ahead and do that. Okay, so we'll have the following, and this thing we'll call message from 3 to 1 of x1. Okay, finally we notice that, well, we can push in the x2 past the phi1 of x1, which doesn't depend on x2, and we could do the same. We could push it past this m3 to 1 of x1. Let me just write that down here. So this thing's going to be equal to phi1 of x1 times m3 to 1 of x1, and then now the summation for x2 of phi2 x2 psi12 x1 x2, and then times these two messages. So the message from 4 to 2 of x2. Let me give myself some room here. Message 5 to 2 of x2. Okay, and so this thing will actually be proportional to the marginal at x1. Okay. Something else to note is that we'll call this thing here, which is, this is the message of, well, we're summing out x2, and this whole thing is only going to be a function of x1. So 2 to 1 of x1. So that's how we can compute this. How computationally what would happen is you begin by computing these m5 to 2, m4 to 2, and m3 to 1. So you compute these three messages. Okay, again, that's 5 to 2, 4 to 2, 3 to 1. Computing each of these amounts to just computing a one-dimensional table. So we do that, and then in order to compute the message from 2 to 1, we need to have first computed the messages from 4 to 2 and 5 to 2. But once we've done that, then we can compute the message from 2 to 1. Okay, and once we have that, we can finally compute the marginal at x1. Okay, so what if we instead wanted the marginal at x3? What do we do? Well, let's just see what changes. First off, we're not going to be doing this summation over x3, right? We're going to instead have a summation over x1. So, well, what does that look like? We take this final expression here, and note that instead of message 3 to 1, we're going to undo, okay? We're going to undo, get rid of the summation. So we'll have phi1 of x1 times phi3 of x3 psi13 of x1 x3 times the message from 2 to 1 of x1. Okay, so this undoes this summation over x3, but then we want to do a summation right over x1. Okay, and so we're going to push in this summation as much as possible. This is going to look like phi3 of x3 times sum over x1 of phi1 of x1 times psi13 of x1 x3 times the message from 2 to 1 of x1. Okay, and so this thing will just be proportional to the marginal for x3 at x3. Okay, and so note the pattern that has emerged. So this thing is, what is this? This is the message from we're summing out x1 to, what is this a function of? Well, it's a function of x3. Okay. Note that the only additional computation really that we need to do is, so these blue arrows denote the messages we've already computed in order to get x1. Now we only have to compute one additional message, namely this message from 1 to 3, which depends on, well, the message from 2 to 1, this 2 to 1 arrow, which depend on these two messages. So we compute this message from 1 to 3, and then now we can compute the node marginal at x3. And so it turns out that we can play the same game and show that, oh, if we just compute the message from 1 to 2, given all the messages we've computed, we'll be able to get the marginal at x2, and then computing the message from 2 to 4 and 2 to 5, we'll be able to get the node marginals at x4 and x5, and that gives us all the node marginals. And that is the sum product algorithm. Okay, so in particular, we compute the messages going from the leaves to a root of our choice, and then we go from the root back to the leaves, passing messages. Okay, and so to write down the general equations, the messages look as follows. The message from I to j is going to be, well, it's a function of xj. We're summing out xi. And if you look at the general pattern for the message computations, it's whatever we're summing over, it's the node potential for that. and then the edge potential between what we're sending, and then the incoming messages. Okay, so sum over phi I of xi, edge potential from I to j, xi xj, and then product over incoming messages to node I except for node j. Ni denotes neighbors of I. Message from k to I of xi. Okay, so this captures all the messages we've computed. Visually, you can think of it as I have node I here, xi and xj. I have a bunch of edges here to other variables. And so to compute the message from node I to node j, I need to consider the node potential at xi, the edge potential between I and j, and then these incoming messages. So these are the messages from neighbors of I, excluding node j. And so we compute this going from leaves to root, and then root back to leaves. And the marginal at node I, so the marginal for xi, well, if you look at what we had before, the marginal was just proportional to the node potential times incoming messages, right? So at node 1, it was just node potential at x1 times messages going into x1. And similarly for x3, it was just node potential at x3 times messages coming in. So in general, the marginal at xi, this is just going to be proportional to the node potential at xi times all the incoming messages. Okay, and so message from k to I is xi. And that's it. This gives you the sum product algorithm, which computes all the node marginals for an undirected tree graphical model.